Okay, in this podcast I'm going to go over the mass, volume, and density worksheet from Unit 2. Okay, so number 1 says study the matter shown in Figure 1. Each dot represents a particle of matter. Assume the particles are uniformly distributed throughout each object, and particles of the same size have the same mass. So what we need to do is compare A to B for mass, volume, and density. Use less than, equal than, or greater than. Alright, so the mass for A, you can count the particles, 8, 12, 13 particles here, more than that here. If they each have the same mass, then the mass of A is of course going to be lower than the mass of B. Volume, the box is smaller for A than it is for B, so the volume is going to be lower. In the density, I can take this box and make it the same size as A, so I have the same amount of space, same volume, and I've got the same number of particles, each have the same mass, so the density here will be equal. Alrighty. Same thing for Figure 2. We're going to compare again mass, volume, and density. So here we have A, B, and C. So the mass of A, the size of the particles are the same. There is less of them in A, so the mass of A is going to be less than the mass of B. In C, there are more particles than A, so the mass will be less in A than it is in C. For volume, A has lower volume than B, but equal volume to C. The density of A and B, if I again take the box of B, I'm going to have the same number of particles as I do in A, so density of A is going to be equal to B, and the density of A compared to C, same volume, more mass with C, so the density of A will be less than C. Okay, now is object E or F more dense? We want to assume particles are uniformly distributed throughout each object, and the particles with a larger size, in this case, these particles here, have more mass than these small particles here. Okay? So if we have the same amount of space, and it looks like we have the same number of particles if you count them, because each of these is more massive, E will be more dense. E will be more dense. Okay, for this question, we have a graph that has substance A and substance B. We've plotted mass on the Y, volume on the X, just like your graphs for your metals lab. It says we have a simple two-pan balance shown above to compare the mass of substance A and B. So the first question is, what would happen to the balance if you put equal masses? Well, equal masses of anything are going to have the same mass, so the pan is going to look just like it does here. So what's going to happen then if you have equal volumes of A and B in the two pans? And it says explain your reasoning. So what I can do is I can take some equal volume, let's say the 30 here, and look at what happens to the mass. So substance B is going to have a mass of 10, right? If I go across, substance A is going to have a mass of 30. So what's going to happen is, for my pan, is I'm going to have the triangle, and A will be down here, and B will be up here, right? A will be heavier. Okay, so what we're going to do here is find the slope for both A and B using the correct units. Okay, so if you remember, the definition of slope is rise over run, right? Or in this case, it's going to be the change in mass, and I use this symbol, this triangle, to mean change. It's also sometimes called the Greek letter delta. Change in mass, which is my y, over change in volume, which is my x. Okay? So let's do it for slope for A, and then we will do slope for B. Alright, so let's first identify 2 points. Now, one of the things we want to be careful about is, let's say I had plotted this as class data, and the computer made a best fit line. But let's say those red dots are the class data, and from that I got this best fit line. When I calculate slope, I want to pick points that are on the line, even if they don't represent data points. Okay, I don't want to pick these because they are not part of the best fit line and will skew my density. So I'm going to pick 2 points. I'm going to pick this point right here, which is on the line. I like to pick points where they intersect one of the blocks and I can easily read the mass or volume. So I'm going to pick this point here at a mass of 80, and let's see, this one intersects pretty nicely here at the 50. Okay, so once I've done that, I can draw then a line. This is one spot, and this would be my other spot, and then I can identify from that the mass and the volume, right? And here is the volume. Okay. Alright, so what I can say then is for A, my initial mass is 80 grams. My new mass is 50 grams. And I look at my change in volume, and it went from 50 milliliters down to 30 milliliters. So here we've got 50 milliliters minus 30 milliliters. Okay, now I can solve, and I end up with 30 grams over 20 milliliters. And if I divide those, I end up with 1.5 grams per milliliter. Now you might wonder why I went with 2 sig figs here and 2 sig figs here. And that's because I can estimate here that this spot is 80. It's not 79. It's not 81. So this is kind of like taking a measurement with a ruler. I know that there are 2 sig figs here. Okay, I can estimate between the lines. Okay, so now let's take a look at B. And I'm going to change the color of my pen in order to do the B lines. Okay, so here's one spot I'm going to use for B, right on the line. And let's say here looks like another good spot. Okay, so from this spot I can draw a line. Whoops, let's make that a line, and I'm going to make it blue. Okay, and then I can take from this spot, I go over to the mass, and I go down to the x-axis for my volumes. Okay, and then what I end up with is, okay, so my highest mass is 40 grams right here, down to 20 grams, minus 20 grams. And my volume goes from, now these numbers are skewed, I apologize for that. It's the same thing on your sheet. This is the 60, this is the 70, this is the 80, and of course this is the 50. Alright, so my volume goes from 80 milliliters down to 40 milliliters. So when we work those, we end up with 20 grams over 40 milliliters, which gives us 0.50 grams per milliliter. See how the units work? It's grams over milliliters, which I can write as grams per milliliter. So the slope of A is 1.5 grams per milliliter. The slope of B is 0.5 grams per milliliter. Alright, so we are on question C, and it says if you put 10 milliliters of A in one balanced PN, how much of mass of B would you need in the other PN? So I can do that 2 ways. I can actually draw a line from 10 milliliters of A, right? I can actually draw it right up through line A and B. And the question is, what is my mass of B going to be? Well, what I got to look at is, what is my mass of A? If I have 10 milliliters of A, I can take that out to the mass axis, and what I looks like I have about, I don't know, 16 or 15 or 16 grams. And if I have 15 or 16 grams, and I want to have the same mass of B, I'm going to need the same amount. So looks like it's about 15 grams. The other thing I can do is use factor label. I can say if I have 10.0 milliliters of A, what I know, because I know the slope now, is I know 1 milliliter of A is 1.5 grams of A, and my milliliters of A cancel out, and I'm left with 10 times 15, which is 1.50 grams of A. And if I want the balance to be even, it's going to also require 1.50 grams of B. Okay, now it says if I put 35 milliliters of B in one balanced pan, what volume of A would you need? So again, I'm going to do this both from the graph, and I'm also going to do it using factor label. So 35 milliliters of B would be right here, right? And that looks like it's about 17 grams of A, right? So that's about 17 grams of B. And the question is, what volume of A would you need? So I actually have that identified right here, because this is 17 grams for A right at this spot. And if I look down, I can plot the volume of A. And it looks like it's just over the 10, so I would call that about 11 milliliters of A. Alright, so let's do it the factor label way. If I have 35.0 milliliters of B, I need to figure out what the mass of that is so I can get the balance to be even. What I know is 1 milliliter of B was 0.50 grams of B, and if I cancel out my milliliters of B, would I end up with 17.5 grams of B? Look how closely that matches. This is an estimate from the graph, and this is a calculation using a density that was estimated from a graph. Okay, so this is 17.5 grams of B, which means I need 17.5 grams of A to make it balance, right? And what I know from my density of A is 1.50 grams of A is 1 milliliter of B. So if I cancel out my grams of A and grams of A, what I end up with is 11.7 milliliters of, this should be A, of A. Okay, so this is question E. It says, water has a density of 1.00 grams per milliliter. And that's something you need to know. That was a defined value. Water was set as the baseline, and everything else is compared to water. So it's 1.00 grams of water per 1 milliliter. And it says, sketch the line representing water in the graph in figure 4. Okay, so if I have a density of 1, what that means is for every 1 milliliter I have 1 gram. So pretty easy to do that. So 80 grams is going to be 80 milliliters. So I'm just going to put a point there. And I can say give any other point. 20 grams is going to be 20 milliliters. Or I can even say 0 grams is 0 milliliters, right? Because if I have no volume, I have no mass. If I have no mass, I have no volume. So let's just make this line. And this is what we're going to end up with. And I'm going to label this water. Okay. So the question now is determine whether substance A and B will float or sink. So substance A is steeper, so it's going to be more dense, so it is going to sink. Just like if you, let's say, put a penny in water, it's going to sink. Substance that is less dense, let's say like vegetable oil, if I put that on water, it's going to float because it is less dense. Okay, question 5 says to sketch a graph of mass versus volume for titanium. Let's see, titanium is right here, copper, and mercury. Okay, so what I need to do is find 2 points that I can make a line from. And the nice thing is, because 0 volume, it gives me 0 mass, is for all of them I can use the 0, 0 point, right? So I can count that as 1 point. So I need to find one other point. I have 10 centimeters cubed here, so what I can do is make this the 10 milliliters, which would be 45.4 grams. I can do the same thing here, 89.6 grams for copper. But for mercury, I can't go for 10 times that amount because it won't fit on the graph. So I've got to use the 5 centimeters. So I'm going to take, if I have 5 centimeters cubed, which is the same as 5 milliliters, because I told you that. What I know is 1 milliliter is going to be 13.55 grams. I cancel those out, and I end up with 68 grams of mercury. Okay, now that we have our points, we can make our lines. So let's see, titanium first, 45, 10 milliliters is 45, so that's going to be about right here, and I can then make my line. That's going to be titanium. And let's make this copper red. So copper will have about 90 grams, so that's going to be about right here. And that's copper. And I will make mercury, let's say green. Alright, so for mercury I'm going to be plotting from 5 milliliters at 68. So this is 50, 60, 70, let's say about right here. And I can make that my mercury line. So let's label these. This is titanium, which is Ti. This is copper, which is Cu. And this is mercury, which is Hg. Alright, there we go. Alright, for question 6, it says we have some cubes made out of each metal, and they measure 2 centimeters on every side, except mercury. Why can't you make a cube of mercury? I bet you know the answer to this, and that's because it is a liquid. Unless you got it really, really cold and got it to freeze. Okay, so what's the volume of each cube in centimeters cubed? Alright, so they all have 2 centimeter sides. If you remember from geometry, volume of a cube is going to be length times width times height. So for all of these, it's going to be 2.00 centimeters times 2.00 centimeters times 2.00 centimeters. I'm going to end up with centimeters cubed as my units. So it's 2 times 2 is 4 times 2 is 8. And I need 3 sig figs, 8 centimeters cubed. And we know that 1 centimeters cubed is equal to 1 milliliters. And you know that because I told you that, not because we have proven it in class. Okay? And then I need to find the mass of each of these metal cubes. Okay, so what I know is I have 8.00 milliliters, right? So for lead, what I know is for every milliliter, it is 11.35 grams. So 1 milliliter is 11.35 grams. And if I do that, I'm going to get, let me punch it, I'm going to get 90.8 grams of lead. Now let's do it for nickel. Nickel is Ni. I have 8.00 milliliters of nickel. And what I know is 1 milliliter of nickel is 8.90 grams. And if I multiply this out, I can cancel out my milliliters, and I'm going to end up with 71.2 grams of nickel. And then the last is zinc. And if I have 8.00 milliliters of zinc, what I know is 1 milliliter of zinc. It has a mass of 7.13 grams. And if I cancel out my milliliters, what I end up with is 57.0 grams of zinc. Alright, question 7. Alicia's cheapskate boyfriend gave her a ring he claims is 24 karat gold. Alicia is skeptical. Well, she should be, because if it's 24 karat gold, it's going to be very soft. After chem class the next day, she measures the mass of the ring, finds the volume of the ring by water displacement, and then calculates the density of the ring. Should she treasure the ring as his first truly generous gift to her, or throw it at him the next day when he walks by? Okay, so what we need to do is figure out the density of this ring, and we can do that by going back, let me see, and looking at the density of gold, right? And density of gold was 19.3 grams per milliliter. So we want to write that down as what we need to compare the density of the ring to. Okay, so what we know is density equals mass over volume. I have the mass, which is 15.28 grams. My volume, I know by water displacement that it went up from 42.2 to 43.7. That difference is 1.5 milliliters. So if I divide this, I'm going to get an answer of, my calculator says 10.2 grams per milliliter, but I only need 2 sig figs. So I'm going to put a dot here to show that I know that this is a zero. It's not an estimate. Grams per milliliter. I could have also put a line over this. Alright, so the ring has a density of 10 grams per milliliter, and the density of gold, AU, is 19.3, way off. So he is a cheapskate for sure. If I look, what I can see is that nickel and copper have a much higher, much closer density to the ring than gold does. And in fact, a nickel is used in a lot of jewelry that's called gold because it's very cheap and it looks similar. So he is a cheapskate and she should throw the ring at him. Okay, so here a student filled a graduated cylinder with water, read the meniscus at 25.8 milliliters. The student then dropped the solid material into the graduated cylinder and the water level rose to 35.9. If the solid material has a density of 2.99 grams per milliliter, determine the mass. So we are trying to find mass. Okay? And we're given enough information to find volume, right? So what I know is we went up to 35.9 milliliters from 25.8 milliliters. So this is a 10.1 milliliter object. So if I have 10.1 milliliters of this object, and I know that the density is 2.99 grams per milliliter, what I know is 1 milliliter is 2.99 grams. Okay, and if I multiply that out, I'm going to end up with 30.2 grams as the mass of the object. Okay, for this question we have some iron, copper, and titanium wires. They're all the same gauge, which means diameter. Your lab group measured out a length of wire that is exactly 10 grams for each type of metal. So the question is, which of these three metals is the longest? Well, I'm going to start by just drawing a simple mass volume chart, and I'm going to just kind of rough in what I think the lines are going to look for each of the metals. So the first is iron. This is iron here, 7.87. So I'm just going to draw that as a line down the middle. And let's say in blue I'm going to do a line for copper. So copper I'll make blue, and it's 8.96, so it's a higher density, therefore a higher slope than the than the iron. And then the last one will be titanium. And titanium, let's say we're going to make that green. Titanium is right here, 4.54 grams per milliliter. Lower density than iron or copper, so I'm going to make the density line for titanium right here. Okay, so then we ask, let me see, we asked which of these three metals is the longest. So if they are all 10 grams, I'm just going to pick some arbitrary point and say, all right, this is 10 grams. And if I go across, what I'll see is the volume of the wire for each metal. Because the diameter is the same, the one that has the longest, the highest volume will also have the greatest diameter. And that will be the green one, which is titanium. Okay? And then which of these three metals will be the shortest? Well, the one with the lowest volume is the blue line, which is copper. Okay. Okay. The last problem is a challenge problem. It'll be more difficult than anything you'll see on the test, although it could be something like a bonus question. It says if every 1 centimeter length of the titanium wire has a mass of 0.15 grams, how long would a 10 gram wire be? Okay. So I have a conversion factor here. I have 10 grams as my, I'm going to make that my given, right? And I have this conversion factor, 1.0 centimeters equal 0.15 grams, right? And I'm trying to find the length. That's my to find. Okay. So if I take that 10.0 grams, and this is titanium, and what it tells me is 0.15 grams is 1.0 centimeters. That tells me that the length is going to be 66.7 centimeters. Okay. Part E is what is the diameter of the titanium wire. Okay, so hint, diameter is related to volume. Assume it's a cylinder. Okay. So the volume of a cylinder, if we remember, is the formula for that is pi r squared times height. All right, we know what pi is, right? We know what the height is. It's 66.7. So diameter is not in here, but radius is, and we can just double the radius to get our diameter. So we need to figure out what the volume is the density of titanium. We know this is titanium, and we know the density of titanium from the graph on the earlier sheet is 4.54 grams per milliliter. Okay, so I can use that. I can say I have 10 grams, and what I know is there's 4.54 grams in 1 milliliter. This is 10.00 grams, right? And if I do that, I'm going to get 2.203 milliliters, which I can also use centimeters cubed of titanium. So this is the volume of the titanium. Alright, so I'm going to take this volume formula equals pi r squared times height, and I'm going to try to isolate the r. And I can do that on this side by dividing both sides by pi times h. Do the same thing on this side. And then what I end up with is r squared equals v over pi times h. Or r is going to equal the square root of v over pi times my h, which I know is 6.67 centimeters. And this v I can replace with this volume, which is 2.203 centimeters cubed. Okay? If I figure out what 2.203 divide by pi times 6.67, I'm going to get the square root of 0.0105, and centimeters cubed over centimeters is going to be centimeters squared. If I take the square root of that, the square root of 0.0105 is 0.102, and the square root of centimeters squared is centimeters. Okay, so that's my radius. If my radius equals 0.102 centimeters, my diameter is my radius times 2, or 0.204 centimeters.